Right, there we are. I'll talk about two areas of research in my presentation that have fascinated me over the past 25 years, namely shell structures and symmetry in structures. What is the connection of these to space structures? Well, shell structures are a type of space structure, since they are lightweight structures that enclose three-dimensional space, with their action generally occurring in three-dimensional space. Although the words shell and spatial structures in the acronym IASS may suggest that shells are distinct from spatial structures, they are in fact actually a subset of the latter. On the other hand, symmetric structures can be 1, 2, or 3-dimensional, but it is within the realm of space structures that symmetry is most abundant and can be exploited the most. Space structures generally exhibit symmetries of high order. We are all familiar with the icosahedral symmetry of the geodesic sphere, which we see in the logo of the Surrey conference. So let me talk about shell structures first of those two topics which I've mentioned. My first formal exposure to shells began some 33 years ago, as I mentioned at the beginning, when I took a course at Imperial College taught by the late Professor Milija Pavlović. Through him, I also became exposed to the ideas of Professor Chris Calladine of Cambridge University, who had been his PhD supervisor, and also the supervisor of IASS President, Professor Pellegrino. At the IASS Symposium of 2018, I joked with Professor Pellegrino about him being my PhD uncle. So just by looking at nature, one became aware of the potential of the thin shell in providing efficient structural solutions. It is not an accident that many natural forms are thin shells, and I'll show examples of that. Seashells, tortoise shells, human skulls, egg shells, snail shells, calabash shells, and goods. Long before the laws of mechanics were discovered, and before the mathematical theories of material and structural behavior were formulated, mankind already had an intuitive sense of the strength and stiffness of the shell form. So we see this in the dome of the Pantheon of ancient Rome, the domes of the Renaissance era in Europe, the domes of the Taj Mahal in India, and even today, the dome-shaped traditional Zulu huts in South Africa. Shells are characterized by surface and curvature, and it is these two properties that give them their characteristic strength and stiffness. So to understand the behavior of thin shells, we first need to understand the geometry of curved surfaces and how forces flow through them. So it was this connection between geometry and structural efficiency that fascinated me. Thin shells find application in many branches of engineering and in architecture. Here are some well-known examples, if I may show you, of shell roofs. The Oceanarium in Valencia, Spain, very familiar. It was designed by the architect, Felix Candela. The roof there comprising thin concrete shells in the form of 8 intersecting paraboloids. Dr. Carlos Lazaro, the vice president of the International Association for Shell and Spatial Structures, was involved in the structural design of this shell. It is a very beautiful shell structure, as you can see, constructed with steel fiber reinforced concrete, and the thickness of the shell is only 60 millimeters. Thus, the interior of an indoor sports dome in Rome, which was designed by Luigi Nevi. This was actually built for the 1960 Olympics, and the dome is more than 60 meters in diameter. The auditorium at MIT in Boston, this was the venue of the IASS Symposium of 2018. This was completed in 1955. Here, the shell geometry is 1/8 of a sphere supported on 3 points. It would be remiss of me not to mention Heinz Eisler's free-flowing shell roofs. These forms were derived by hanging pieces of cloth and observing their shape under gravity. Other examples, which I can mention very quickly, are as follows. Concrete ash dams, such as the Kasi Dam in Lesotho, liquid storage steel tanks, elevated water tanks, egg-shaped sludge digesters, such as these structures here under construction in Pietermaritzburg, South Africa. As is well known, rigorous formulations of shell theory often lead to differential equations, which are quite difficult to solve exactly. So numerical techniques provide a means of arriving at approximate solutions. But unfortunately, they are not always the best in providing a deeper understanding of shell behavior. So one strategy is to aim for approximate but accurate analytical solutions. We may either make simplifying assumptions at the beginning of our formulation, or we may introduce simplifying approximations in the final stage, in the final set of the governing equations, rather. Besides providing useful insights on shell behavior, closed-form solutions also allow parametric studies to be undertaken and the effects of design changes to be more clearly understood. So a significant proportion of my research has concerned the development of analytical methods for novel types of shell applications with liquid containment in mind. These have included new forms of egg-shaped sludge digesters and multi-shell assemblies for large capacity liquid containment. And as much as possible, we try to achieve a membrane state of stress and avoid bending of the shell, as membrane action is more efficient than bending action. Much less material is required to resist membrane action than to resist bending. But where bending cannot be avoided, we want to be able to quantify the magnitude of the bending effects and try to minimize these. And where membrane compression prevails, we also want to make sure that buckling of the shell will not be a problem. You will find some of this work reflected in the new edition of my book, which is called Shell Structures in Civil and Mechanical Engineering. This was published in 2018 by the Institution of Civil Engineers. Before leaving the subject of shells, let me just mention a project that was designed by a Cape Town structural engineer, whom I have known and interacted with for several years. This is the Bosjes Chapel near the town of Worcester in South Africa, which was completed in 2016 and featuring quite an unusual shell roof. The shape of the shell was prescribed by the architect, and I know the structural engineer was not too happy with the relatively large bending moments that this shape attracted. So there were areas of the shell that relied on bending to carry the loads, and the shell had to be quite thick, especially around the supports. So the shell was supported on 4 short vertical columns, which I'm going to show you very shortly. The formwork was complicated, as you can see in this photo. Conventional concrete was used for the thicker zones that were near horizontal, while shotcrete was used for the sloping regions. The greatest challenge here was actually controlling the accuracy of the shattering and fitting reinforcement to a rapidly undulating surface. You can see where the columns are in this slide of the finishing stages. But in the end, the result was an impressive structure, and the project has won numerous architectural awards. I will now talk about my second topic, which I mentioned, which is symmetry. My research on applications of group theory to problems in structural mechanics has involved formulating problems of the vibration and statics of cable nets, grids, plates, and space frames in such a way as to take maximum advantage of the full symmetry of the structure. So let me just start off very quickly by basic definitions. What is symmetry? A structure is said to exhibit symmetry if it can be turned into one or more configurations that are physically indistinguishable from the first. Okay, through the applications of various symmetry operations, such as reflections, rotations, inversions, rotary reflections, and so forth. Group theory. This is a mathematical approach that provides a systematic means for studying and exploiting symmetry in physical systems. You may think of it as the mathematical language of symmetry. So group theoretic formulations are particularly advantageous in the analysis of large-scale structures, which are characterized by repetitiveness, cyclicity, and other more complex types of symmetries. So when they are applied to the vibration analysis of symmetric systems, the group theoretic formulation allows the space of the problem to be decomposed into independent subspaces which are spanned by symmetry-adapted motions. So the symmetry-adapted motions become the basis vectors. What do we mean by that? They become the unknowns of the subspaces. This permits the eigenvalues to be calculated through the solution of relatively simple equations. So our studies in terms of applications have included cable nets. Details may be seen in these two publications, which I can show you very quickly. The first paper appeared in the Transactions of the Royal Society, Part A, while the second is a more recent study in solids and structures. Double layer and triple layer space grids. Here are examples of subspace basis vector plots for a simple triangular space grid and a simple hexagonal space grid. Notice that the basis vectors of a subspace all have the same symmetries that are characteristic of the subspaces. For the simple triangular space grid, which I've just shown, the vibration modes that were obtained using this approach look something like this. And as with the basis vectors, we see that the symmetries of the vibration modes are characteristic of the subspace to which they belong. Details of these studies may be seen in the following publications. The two papers appeared in Engineering Structures. The first emphasized insights and qualitative benefits, while the second illustrated computational steps and presented some numerical results. The book Vibration Analysis and Structural Dynamics for Civil Engineers, Essentials and Group Theoretic Formulations was published by CRC Press, Taylor and Francis in 2015, and it collects together some of these various studies. In summary, the benefits of using group theory to study the vibration of symmetric space structures are as follows. First of all, the simplification, a reduction of computational problem. We also acquire prior knowledge of all possible symmetries of the modes. We also get a prediction of the number of modes of a given symmetry, prediction of nodal lines and stationary points of a system. All these are very, very valuable properties of the vibrating systems. Identification of modes of the same frequencies, untangling of frequencies, and avoidance of numerical difficulties. Sometimes symmetry in space structures is not immediately obvious, or some of the symmetry properties may not be easy to identify. So to address this problem, I've also been working on the development of algorithms for the automatic recognition of symmetry in structures. Another new direction of the work on group theory is the use of symmetry groups as a tool for rapidly generating complex space grids. The advantage of this approach is that the final configuration has predetermined symmetry properties. So just to illustrate this idea, quickly consider this example here. We start off with a simple pyramid unit on the extreme left. We can then apply elements of the symmetry groups C1V to begin with, followed by C4V, which is like the symmetry of the square, and D2H respectively, which rapidly, in just 3 steps, gives us the fairly complex triple layer space grid, which you see on the extreme right. This has 832 members and belongs to symmetry group D4H, which takes me to the end of this presentation.